Hey everyone, and welcome to our fourth and final video lesson for lesson 3.2. This is going to be obviously a very information-packed lesson, so rather than condensing everything down into one or two videos, just making sure we did a little bit at a time here. But you can see that from the highlighted learning targets, we only have one left to go, and that is to describe how a least squares regression line, the standard deviation of the residuals, and R squared are influenced by outliers. So if we scroll down to our last set of information here, we've got some final reminders about correlation and regression. So first, correlation and regression lines describe only linear relationships. We've talked about that before. If it's not linear, then there's no need to do any of this. So always plot your data in a scatter plot before determining correlation in your least squares regression line, because if the plot is non-linear, then you do not use linear regression to find the correlation. We will talk about in a later lesson, what do we do if it's not linear? But for right now, if it's not linear, then don't use it. Next, correlation and the least squares regression line are not resistant. So remember, what that means is that extreme values will have an effect on our various measures. So what we want to know is, how do they affect our measures? So what we're going to do is run through a series of possibilities here. You do not need to follow along on your calculator per se, because there's just going to be a lot of minor changes and stuff like that. So what I really want you to take note of is on my screen, what's going on, making sure you're getting the concepts written down, things of that nature, but by no means do you need to follow along by punching in all of these things on the calculator as well, okay? So it saves you a little bit of time. So example 12, it says, using the data in the table below, calculate the least squares regression line, R squared, and the standard deviation of the residuals, sketch its scatter plot with the least squares regression line included, scale both axes from 0 to 35 by 5. Okay, so just so you can kind of see, I already have that data in my list 1 and list 2. Okay, so first thing it tells me to do is to calculate the least squares regression line, R squared. So all of those can be found, stat, calc, option 8, linear regression. So my least squares regression line is going to be y hat equals 3.43 plus 0.59x. So calculate least squares regression line, check. My R value is 0.39 or 0.39, so not very strong. My R squared value, which is just my R value squared, 0.15. And then my standard deviation of the residual. So remember, in order to do that, now that I've calculated my least squares regression line, I'm going to go stat edit.
Carhartt.
Of course, there's going to be an error or an add. So let's try this again. Stat edit. And I have data for L3 and L4 later. So I'm just going to jump over here to L5. I want L5 to equal my residuals. So second stat, option 7 is residuals. And then what we do in order to find the standard deviation, now that all of my residuals are there in list 5, I'm going to do my one variable stats, stat calc one variable stats on list 5. There we go. And I can see that my standard deviation of the residuals is 2.67. So the next thing that I'm going to do is sketch the scatter plot with the least squares regression line included. So go to my calculator, it said to scale everything from 0 to 35 by 5, so you can see my window is set up there. And then I'm going to have plot 1 on as a scatter plot, pulling from list 1 and list 2. And I don't need to have plot 2 on. So there's my scatter plot, but it said it also wanted to have the least squares regression line included. So I'll go into y equals 3.43 plus 0.59x. That was the equation that we just got from our calculator. So if I were to graph that, we can see this picture here. So pretty condensed down in the right-hand corner. Point, 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 point. And our line looks to go something roughly like this. Okay. So there's our original set of data. Now, the next thing it's going to ask us to do is add this point, 3524, to the data set. So, I'm going to edit list 1 and list 2. And I'm going to include the point 3524 to this data set. And then once again, calculate all of the same stuff we did before. So now that I've added that, I'll calculate my least squares regression line, stat calc, option 8. And now I can see that my equation, switch to a new color here, is going to be 3.43 plus 0.59x. Which is the exact same equation. However, look at the R value. We went from 0.39 to 0.93. Significant increase. Okay, we can see that our R squared value also had a significant increase. And then if I quickly calculate my residuals again, and stat calc one variable stats on list 5. My standard deviation is, or standard deviation of the residuals, 2.5. So not drastically different here. So what is it about this one point here at 3524 that really just affected correlation and not much else? Well, if I go back to my graph, we really can't see 3524 specifically, or it's really tough. If you look all the way at the end of our blue line, you'll see the smallest of dots. Okay, that's at the point 3524. So notice it's on the least squares regression line that was already generated. Okay, and that's important. So this point is far away from all the other x values. So think about like an extrapolated value. However, it's following the same pattern as all of the previous x's. And so that's why the slope really didn't change. That's why our standard deviation of the residuals didn't really change, because we were following the same pattern we had before. But what we did was we added a new point that was ridiculously close, pretty much on top of our original line, which gives more credence to that line being accurate, and that's why our correlation is so much stronger. So now, if I just take this and duplicate it, but we added this point right here on the end. Here's how we would comment. Okay. When an x value is far from all other x values, but follows the same pattern, the correlation strengthens and nothing else is significantly altered. Here's kind of an outlier value, right? We want to know what effect do outliers have on this information. Well, if it's still following the same pattern as the rest of the data, then it's not going to affect too much other than it's going to strengthen the correlation big time. Okay? Because it's also facing this or following the same pattern, we'll notice that it didn't really affect the equation of the least squares regression line, right? The slope didn't need to change. The y-intercept didn't need to change. Okay? So really it's just the correlation. So now, part B, replace that point that we just had of 35.24 with 35.2. So essentially what's going to happen is this point here is just going to drop down to there. And let's see what happens. So we're going to edit this and we're going to go to the point 35.2. Calculator's not cooperating much today. 35.2. Okay, and what you'll see if I just go to the graph really quickly, again, you really can't see it all too well, but at the very end, the very right side of the graph, you'll kind of see a little blue dot underneath, significantly underneath our least squares regression line that we originally had. So that's what the new scatter plot looks like. So I'm going to take this. Actually, I'm going to redo that. So that purple line is our original, but now we've got this point down here. So I want to know, how is this going to change? And maybe this is a good brainstorming activity. So this purple line was for the original data. So take a moment to think to yourself, what is this going to do to our equation? What's it going to do to our slope? What's it going to do to our y-intercept? What do you think is going to happen to our correlation? Thus, what's also going to happen to our r-squared? And what's going to happen to the standard deviation of the residuals? So let's find out. If I go to our calculator, and now I calculate our least squares regression line with this new data, we can see that we have 5.83 excuse me, minus 0.09x. So notice the y-intercept increased. The slope obviously decreased. And that should make sense because now we have to try to bring this down in order to get to this red point. Well, in order to bring that down, to balance it, this side would have to come up. That's my y-intercept. So my y-intercept increases while my slope decreases. we can see that the R value is negative now, and it's 0.34. So it weakened. R squared value, 0.11. And my standard deviation of the errors, stat edit list 5. And then stat, one variable stats. Standard deviation of the residuals, 2.79. Okay. So when we look at this red information from this point compared to this purple information from our original data set, we can see that the correlations really weren't heavily altered in this case in terms of strength, but certainly in direction. Okay, so it was altered for sure. The standard deviation of the residuals wasn't heavily affected, but the biggest impact was on our least squares regression line. Okay, so when an X value, and we're going to use kind of the same wording as before, is far from all other X values, again, extrapolated value, and doesn't follow the same pattern. Okay, so that's what we have here. It doesn't follow the same pattern. The correlation weakens. And the least squares regression line alters to reach the new, or I guess I'll say the extreme point. Okay, it's going to alter or adjust to reach that extreme point. And there is going to be that inverse relationship with slope and y-intercept, right? This line has to come down. The slope has to adjust. So the slope is going down, but in order for that to happen, the y-intercept would have to increase. So there's going to be that inverse relationship. Y-intercept will go up, and that will lower the slope. Or the y-intercept could go down, and that would lift the slope up, depending on what the original data and the new point look like. So just kind of keep that idea in mind. All right. Lastly, we're going to replace the point 35.2 with the point 435. And then again, take these steps one more time. So if I take just the original data, so we have right here. There's the original data. Now, if we think about 435, well, if I look at these X values here, 4 is about halfway in the middle, but 35 is obviously significantly higher. So what we're thinking is we're going to get something that's like right there. Let's switch this to orange. So what I want to know is what's going to happen to my line here? What's going to happen to my correlation? What's going to happen to my standard deviation of the residuals? Okay, so take a moment and think about that for yourself. What's going to happen? Okay, so now let's take a look. If I pull up this information one more time, and I'm going to replace 35.2 35.2 is going to get replaced with 435. We really can't see the full dot, But if you look straight up from the middle of the cluster of points, way up above our least squares regression line in blue, you can see kind of that blue partial square. So that's the point that we just added. So now let's see, what did that do in terms of all of our calculations? Stat calc option 8, linear regression, 5.31 plus 0.96x with a correlation of 0.17 and r squared of 0.03. And my standard deviation of the residuals will be, sorry, I know this takes a while. Standard deviation of the residuals is 10.03. So now, if I take this information and compare it with the original information, I see completely different equations of lines. I see a weak correlation remaining weak, but I see a significant difference in terms of error. And if I were to graph really quickly this new line that we just calculated as well, which was 5.31 plus 0.96x, you see that in red, you can see that it's not drastically different. Maybe that's surprising to you, but it's not drastically different. Okay? The y-intercept didn't shoot down in the slope did not drastically shoot up. And that's because of where our x value is. In our previous two examples, x was extremely larger than the rest of them. It was at the end, and therefore we had a responsibility to generate a line that took that point into account. And a line has to get us from start to finish. But in this case here, this extreme value wasn't with the x, it was with the y. The x was perfectly normal. And so because it's in the middle of our cluster, our red line here is still doing its responsibility of capturing the start of the relationship and the end of the relationship. But it was lifted a little bit to get up towards that extreme y value. Okay? So what we have to kind of recognize is when we have an outlier, is the extreme value the x coordinate or is it the y coordinate? And we'll kind of summarize that all in just a moment. Okay, so in this case here, we can say something like when the x value is similar to the others, but the y value is significantly different, the biggest change is in our standard deviation of the residuals. Because if you think about our residuals, it's here, 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 here. But then now we've just added this one really large one. So when the x value is similar to the others, but the y value is significantly different, the standard deviation of the residuals is greatly increased. So here's how we identify these concepts. Influential points. Any point that, if removed, substantially changes the slope, the y-intercept, the correlation all of these calculations, right? That's what we consider to be an influential point. If we were to take it away, or if we were to alter it, then it has a significant impact on some of, if not all of our calculations. So in parts A and B, as I mentioned, we call these high leverage points. In high leverage points, the X value is the extreme one. That significantly differs from the rest. It's much larger or it's much smaller than all of the other X values. And so we have this note that we summarized before. High leverage points that follow the pattern of the rest of the data will increase the correlation, whereas high leverage points that differ from the pattern will decrease the correlation. Okay, and that's what we had in these two examples. The X value was the extreme one. However, part C provides us with an example of an outlier. Okay, this is a point that doesn't follow the pattern and has a large residual. Okay, and that's what we would have here. This was an outlier. The X value was an extreme, but its corresponding Y value was. And when that happens, the standard deviation of the residuals is increased. Now, last example that we are going to do, again, you don't need to put this into your calculator. I'll take care of that for you. But in example 13, below is the table of a year in American history. So we can see that right here. The number of ministers in New England that year, and the number of barrels of rum imported into Boston that year. And so what I'm doing is I put this into, I'll write list 1 and list 2, but for me it's actually list 3 and list 4. And we're going to do some calculations with this really quick. So the first one, determine the correlation between the number of ministers in New England and the number of barrels of rum imported. Okay. So if I take a look here, if I show you this, stat, edit, you can see it's my, no, you can't because calculator's frozen. Stat, edit, it's in my list 3 and list 4. Okay, so it asks us to calculate the correlation between these things. So stat, calc, option 8. We want list 3 and list 4. And I can see that the correlation is 0.99996. R equals 0.99996. Okay, almost a perfect correlation. And in fact, if I were to make the scatter plot for that, change this to list 3, change this to list 4, zoom 9. I gotta turn some stuff off here. Let's try this again. There we go. Okay, you can see that it's almost a perfectly straight line. So then, what percent of variation in rum importation can be explained by its linear relationship with the number of ministers in New England? What percent of the variation? That's a fancy way of saying what is R squared. So if I go back to the calculator, I can see my R squared value was, again, 0.99991. Therefore, 99.99%. What percent of rum importation can be explained by its linear relationship with the number of ministers in New England? Almost 100%, which means that the number of barrels of rum imported into New England on any given year was 100% based on the number of ministers that there were. Okay. Now, we all know that our ministers love to party, but the realistic approach here is this should set off a little red flag saying something's not right with this. Well, everything is right. There were no errors in the calculations or anything like that. But we have to come back to this concept that correlation does not imply causation, right? It's not necessarily that, oh, we've got more ministers, that means more rum is coming in. we always have to consider lurking variables before we draw conclusions. So by definition, a lurking variable is a variable that's neither the explanatory variable nor the response variable, yet may have an influence on their relationship. And so in this case here, we think about the years that are going on. Well, this is, early American history. What would be going on? Well, the population in general is increasing. Okay, so as the country is growing, there's more of everything. There's more ministers, there's more rum, there's more horses, there's more houses, there's more everything. So although there's a very strong relationship between the number of ministers and the number of barrels of rum, there's a extremely strong correlation, but it's not causation. Okay, one is not causing the other to happen directly. So it's always important to think of lurking variables. So what I want you to do is, as we read through example 14, think about some potential lurking variables that might exist that could affect our relationship. It says that a study is conducted to determine the relationship between activity level and the risk of heart attack. What are some lurking variables that should be considered? So see if you can come up with a list of about 5 things here, and then we'll share out. Okay, so things may be age, could be gender, it could be diet, it could be genetics, okay, it could be race. Another one that's come up in years past has been stress level. These are all things that are neither activity level nor risk of heart attack, but could have an effect on the risk of a heart attack. So, thank you all for your patience as we worked through 3.2. As always, if you do have any questions, please let me know. Otherwise, take care, and we'll see you next time.